Okay, here's again a small simple multi-step synthesis problem involving some conversions, and it's going to be rather straightforward, but the molecule looks a little complicated because of its polycyclic structure, but you don't have to worry about that or get distracted by that. If you look at the functional groups, you can clearly see what's going on. So this is an alkane with a keto group, and you're converting your ketone to an ester, and we know that if you want to insert an oxygen, then you should use MCPBA or some sort of peroxy acid. MCPBA works for both epoxidation and also for converting your keto to an ester group, which is what you call the Baeyer-Villiger oxidation. So this is the peroxy acid. Okay, again, it doesn't have to be MCPBA, it could be any peroxy acid, and that inserts your oxygen on the on one of the sites. Since it's a symmetric molecule in terms of a symmetric functional group, I would say, because both sides it's just a carbon like of the same degree. This is a secondary carbon, therefore it's going to be the same. So you'll insert your oxygen on one of the sites. That's what the oxygen that comes from the Baeyer-Villiger oxidation is. And now you converted your ester here to two alcohols, and you know what's going on here. It is going to be lithium aluminum hydride reduction followed by acidified water treatment, okay, for water workup. Okay, so you have done that. Now you have a primary alcohol, secondary alcohol. If you use tosyl chloride, you will actually if you have excess tosyl chloride, obviously you're going to tosylate both the alcohols. But if you have only one equivalent and do this in a controlled manner, then you will be able to convert your primary alcohol into a tosylate than a secondary alcohol, because the primary alcohol is less hindered. Okay, so therefore that alcoholic group here, the primary alcohol, is converted to the corresponding tosylate, and pyridine, as you know, is the base. And in case you don't remember the structure of tosyl chloride, it is paratoluene toluene sulfonyl chloride. Okay, sulfonyl chloride, this is CH3, and the chlorine leaves and the oxygen acts as a nucleophile, and you make a sulfur oxygen bond. So the TS is this group here. Okay, all right, so that's that. Now what you're seeing is you are closing the ring. That's the OH group that you see here, and then this is your OTS. And as you can see, the OTS is going to be a really good leaving group which takes this oxygen along with it. So if you are not able to see it, that's essentially the group we are talking about. That is the OTS. Okay. So once you attach a tosyl group to the oxygen, it makes it a good leaving group because it can take these electrons and be able to manage the negative charge very well. Therefore, the oxygen previously as an OH is not a good leaving group, but now it is a good leaving group. So once you have a good leaving group, this alcohol can act as the nucleophile and let this carbon oxygen bond break, and that's the ring closing you're seeing. But if you want to facilitate this, then converting your alcohol that is free here into a alkoxide is going to make it more efficient, and you can do that by adding something like sodium hydride. You add sodium hydride, the sodium hydride will deprotonate this alcohol, make it an alkoxide, and now the alkoxide can act as a nucleophile to let this tosylate group leave along with the oxygen that was previously in the molecule. Okay, so that what is going to cause the ring closing here.